Hello, everybody. I'm Karen Voetman. I'm here to introduce the next plenary speaker in this ICM, who's Mladen Bestvina. So Mladen got his undergraduate degree from the University of Zagreb in Croatia, and then went to the United States to get a PhD from the University of Tennessee. He became a tenured faculty member at UCLA and then moved to the University of Utah, where he's been since then and now holds a distinguished professor chair. So Mladen's work has had a profound impact on topology and geometric group theory. So this includes spectacular advances in the theories of Gromov hyperbolic spaces, mapping class groups, and Artin groups and automorphisms of free groups, among other things. He's sort of a master at finding a way around seemingly impassable roadblocks that have stymied everyone else working on a problem. So in the course of solving these difficult problems, he's invented a lot of powerful new geometric techniques, such as the theory of train tracks for understanding automorphisms of free groups, the metric theory of outer space, Bestvina Brady-Morse theory for understanding finiteness properties of groups, a combination theorem for hyperbolic groups, and so on and so forth. The techniques he's introduced have now become part of the standard toolbox that you issue to every newly minted geometric group theorist. So he's received many tributes recognizing his exceptional talents, starting with 3 medals in the International Mathematics Olympiad when he was a teenager. I won't give details, but just say that they include being invited to give numerous prestigious lectures and lecture series around the world, including a sectional lecture at the 2002 ICM in Beijing. And today he's going to give us a survey of groups acting on hyperbolic spaces. There won't be a question period after this talk. People with questions are invited to contact Mladen by email.
Thank you, Karen, for this wonderful introduction. Hello, everybody. It's a great pleasure and honor for me to be here, and I'd like to thank the committee for the invitation. And I would like to thank all of you for tuning in. So the talk is going to be a survey talk about groups acting on hyperbolic spaces. This is really part of the relatively new subject called geometric group theory, which uses tools from geometry and topology, at least classically, to study discrete groups. And increasingly, it also uses tools from other fields like analysis and dynamics. The subject was started by some remarkable papers of Misha Gromov in the 80s. And the basic message that he told us was view groups as metric spaces. Okay, so my plan here is to first explain what it means to view groups as metric spaces. And then I'd like to talk about this key idea of hyperbolicity. So here you see 3 triangles. The leftmost triangle is a triangle on the sphere whose sides are all geodesics. So it's a geodesic triangle on the sphere. It looks fatter than the planar triangle in the middle. And then the hyperbolic triangle made up of geodesics in the hyperbolic plane looks thinnest of all. And that's the idea that somehow leads to the abstract notion of a hyperbolic metric space. The subject was initially focused on hyperbolic groups, that is, groups which as metric spaces are hyperbolic. And I will explain some key results from that period. But somehow the fundamental shift that occurred around the year 2000 was that we realized that some non-hyperbolic groups of great interest in geometric group theory can be understood by looking at their actions on hyperbolic spaces. And I also like to think of subjects in terms of constructions. And so here there's a construction that's very useful in the subject, where one can build new hyperbolic spaces where given groups act. And that's the idea of projection complexes. So I will try to explain how this works. And in particular, I will explain some applications of this construction to two classes of groups that I like very much. One is the mapping class groups. So these are, you could think of them as symmetries of surfaces. They're really homeomorphisms of surfaces modulo homotopy. And and then out Fn, that's for a topologist like me, you can think of out Fn as being a group of homotopy equivalences of a graph whose fundamental group is free group of rank n. So here the graph pictured has fundamental group F2. Okay, so let's start with this plane. So first, I want to tell you how to think of groups as metric spaces. This is in fact a very classical concept that goes back to the notion of Cayley graphs. So you have a group G, and we'll always assume that our groups are finitely generated. And in fact, it's convenient to take a generating set that is symmetric. So if we have a generator, then its inverse is also on the list. So that's the set S. And then from the set S, you can define a word norm. So this is some kind of a norm on this group G. And it's defined by looking at, so G is a group element, and you look at the minimal integer K so that you can write G as a product of K generators here. Okay, so then you say that the norm of G is K, that's the smallest possible K. And then the related metric is just, so the distance between G and H is just the norm of G inverse H. And that's set up in such a way that when you look at left multiplication by a fixed element, like in this case A is some fixed element of the group, and you look at the bijection of the group that sends the group element to let you multiply on the left by this element A, well, that's an isometry. And to help visualize this, you can think about the Cayley graph. The Cayley graph has a vertex set, the group itself, and then you put an edge between two group elements if they differ by a generator. So a group element G is connected to the product of G with any of the generators. And this is because S is a symmetric set, S equals S inverse. This notion here is symmetric. Okay, so so here are two well-known Cayley graphs. Here's a free group of rank 2, where you get a tree, infinite tree. On the left here, and on the right is the fundamental group of the genus 2 surface. And it's conveniently drawn in the Poincare disk, in the model of the hyperbolic plane. And geometrically, this fits because a genus 2 surface can be endowed with a hyperbolic metric so that its universal cover is in fact a hyperbolic plane. And you can see that that here on the right, what appears as cycles here, as closed cycles, are exactly the relations in the group. Okay, and then you can visualize the word metric as being just a distance in the Cayley graph. I take two vertices in the Cayley graph, and I'm interested in computing the distance, that d sub s, the distance given by the generating set. Well, I could, that equivalently, I could just think about finding the shortest possible path in the Cayley graph from one vertex to the other. Okay. Now, what happens if I decide to use a different generating set? Well, then I have the identity map from from G to G, but on one side I'm thinking of it with the metric given by S, and on the other side I'm thinking of it as the metric given by S prime. Well, that is it's not too hard to see that this identity map is in fact a bi-Lipschitz with respect to two different metrics. And so you could say, well, a group here is endowed with the metric up to bi-Lipschitz equivalence. But in fact, it is useful to consider a weaker notion of equivalence. And this weaker notion is called a quasi-isometry. So there's a notion of two metric spaces being quasi-isometric. And this is generated by two operations. One is the bi-Lipschitz homeomorphisms, like in this case above, with two different generating sets on the same discrete group. And then the other one is the co-bounded inclusions. So here, X and Y are two metric spaces. Y is a subspace of X. and we'll view it as with the induced metric. So where there's a metric on X, and we look at the induced metric on Y. But we assume that this inclusion is co-bounded, meaning that there's some big number R, so that if you take any metric R ball in X, it will intersect Y. So in this kind of metric sense, Y is coarsely dense. So for example, I can look at the integers in the real line. And so this definition will tell me that the inclusion from Z into R is co-bounded, and therefore Z and R are quasi-isometric, and that's what I wrote here. And more generally, you can take a finite index subgroup over the discrete group, and then they're going to be quasi-isometric because this inclusion will be co-bounded. Okay, now we come to a theorem that's commonly regarded as being the fundamental theorem in geometric group theory. And it's due to Milner and Schwarz. So the setup is this. You have a metric space X, which we'll assume also is proper and geodesic. Proper here means that every closed metric ball in the space is compact. Okay, so that's a stronger notion than saying that the space is locally compact. It's a metric version of local compactness. So for example, Euclidean plane is a proper metric space. And then geodesic means that any two points in the space are connected by a geodesic, namely by an arc. They're connected by an arc, which is isometric to a segment in the real line whose length is given by the distance between the 2 points. Okay, so those are assumptions on the space X. And then we have a group G acting by isometries on the space X. And the action is co-compact, meaning that given that there exists some compact subset of X whose translates by G cover all of X. And the other thing is that the action is assumed to be properly discontinuous, meaning that given any compact subset of X, there are only finitely many group elements that take this compact set to another set that intersect the original set. Okay, and then under these assumptions, the theorem of Milner and Schwarz is that, first of all, G is a finitely generated group, and so you can equip it with the word metric, as explained before. And then the second part of the theorem is that, in fact, with that metric, G is quasi-isometric to X. Okay, so somehow geometrically, there's no X is a good model for the group G if you're interested in the coarse geometry of the group. And so, for example, you've already seen these two pictures. The free group F2 is acting on this tree over here, and the assumptions on the space and on the action are satisfied. And so we conclude that the free group is in fact quasi-isometric to this tree. And likewise, the fundamental group of the surface of genus 2 is quasi-isometric to the hyperbolic plane because it is acting in a suitable way on the universal cover of the surface. Similarly to Z being quasi-isometric to R, we see that Z to the N is quasi-isometric to R to the N. And also more generally, co-compact lattices in Lie groups are quasi-isometric to their symmetric spaces. Okay, so that's the basic definition and the basic concepts about viewing groups as metric spaces. And now we turn to the notion of hyperbolicity. So this definition is due to Rips, and there are various other equivalent definitions due to Gromov. Okay, so we start with a geodesic metric space. Okay, so we have a geodesic metric space, and so we're going to look at geodesic triangles in the space. And we want to know that every geodesic triangle is uniformly thin. So there's this parameter delta that determines how thin a triangle is. So you should think of it as being fairly big. It can be as big as you like, but it has to be the same number for all triangles. And so what the definition says is that for every geodesic triangle, if you look at one side, for example, AB, here's a geodesic connecting A and B. By the way, these geodesics don't have to be unique. But this is supposed to be true for every choice of a geodesic between any two of these points. Okay, so you take a geodesic from A to B. Well, it's supposed to be contained in the delta neighborhood of the union of the other two sides. Okay, in other words, if you think about taking the delta neighborhood of, say, the side AC, well, that looks something like this. And then you take the neighborhood of the side, delta neighborhood of BC, and it'll look like this. Well, this union has to cover the side AB. Or you should maybe think of it as you're walking from A to B, and at every moment you're going to be uniformly close to one of the two sides. So at some point you're switching from one side to the other side. But delta is roughly the distance, the largest distance as you walk from A to B to the union of the other two sides. Okay, so then we make a definition for when a group is hyperbolic. So we say that a finitely generated group is hyperbolic if its Cayley graph is delta hyperbolic for some delta. And then, of course, you might wonder how dependent is this on the choice of the generating set. And then luckily, there's the Morse lemma, which says that it doesn't depend on the finite generating set, because if I have two spaces, two metric spaces, they're quasi-isometric and they're both geodesic metric spaces. And one is delta hyperbolic, then the other one is delta prime hyperbolic for some possible larger delta prime. So choosing a different generating set, of course, will give me a quasi-isometric metric on the same group, and therefore they're either both hyperbolic or neither. Okay, so what are some examples here? Trees are hyperbolic, and there's zero hyperbolic. They're as hyperbolic as one can get. That is, if I think about so here's a tree. If I think about taking three points and joining them by geodesics, well, the geodesic triangle is going to be degenerate. It will be a tripod, and so you can see that the required delta is in fact zero here. And therefore, free groups are also hyperbolic because they're quasi-isometric to trees. A hyperbolic plane is hyperbolic. Triangles in hyperbolic plane on the hyperbolic plane are thin, uniformly thin, and more, similarly, hyperbolic n space is going to be hyperbolic. And therefore, fundamental groups of orientable surfaces of genus greater or equal to 2 and co-compact lattices rank 1D groups. That's all because they act on spaces that are hyperbolic in the sense of differential geometry. Curvature is strictly less than 0, uniformly bounded away from 0, and therefore by the Milnor-Schwarz theorem, they're going to be hyperbolic. There are also various constructions. For example, free products of hyperbolic groups are going to be hyperbolic. There are also certain kinds of amalgams, although then you have to make some assumptions on what kinds of amalgams, but we know how to construct lots of hyperbolic groups. There's also an interesting fact that in some sense random groups are hyperbolic. So there are many different models for random groups, but the simplest one is this. Maybe you fix the number of generators, maybe say 2, and you fix the number of relations. So let's say 3, okay? And now for any integer n, you look at all possible presentations of groups with 2 generators and 3 relations where all 3 relations have length n. And you look at the percentage of those presentations that define hyperbolic groups. And so the theorem is that as n goes to infinity, as the length of these relations goes to infinity, the percentage of hyperbolic groups goes to 100. So if you choose large n, then it's very likely that your group that you write down some random presentation that it will be hyperbolic. Well, not all groups are hyperbolic, of course, and the basic non-example is Z2. That is, Z2 is quasi-isometric to the Euclidean plane, and in the Euclidean plane, triangles are not thin. You can take a triangle like this, and there's certain delta that's required for this, but then you can also scale it up, and you can see that no finite delta will suffice for all geodesic triangles in the plane. And in fact, this Z2 is a Poisson subgroup. So if a hyperbolic group, so no hyperbolic group contains Z2. So if you have a group that contains Z2, then it's not hyperbolic. Okay, so here I kind of listed some properties of hyperbolic groups. There are many more that I'm not going to feature here. So for example, from a point of view of a topologist, maybe the most interesting one is the second one here, the second bullet. If the group is torsion free and it is hyperbolic, then in fact it has a finite classifying space. And then more generally, if you don't assume that the group is torsion free, well, then it will have finitely many conjugacy classes of finite subgroups. In fact, a better way to think about this is that there's going to be a finite classifying orbifold. And these finite subgroups will appear as stabilizers of points in this model classifying orbifold. This is all proved by construction of RIPS, which says that if you have a hyperbolic group, then you can find some number, say D, much larger than your delta for that group, so that if you glue in a simplex to every finite collection of vertices, so that the pairwise distances are less than this number D, then in fact you get a contractible space, and the group is going to be acting on this contractible simplicial complex, and and then these results will follow. The dynamics of the action on itself, so group is acting on itself by left translations, by isometries, is also well understood. Every element of infinite order, for example, is loxodromic. So what does loxodromic mean? So the model case is when you have an element it's acting by isometries in the hyperbolic plane and preserving some geodesic line and translating along that geodesic line. So here, there's a coarse analog of this concept of translating along a geodesic line. Namely, if you take an orbit, so you fix some base point and you look at the orbit of this point by a fixed element G of infinite order, well, what you see, that orbit is going to be quasi-isometric to a line. So these points will be marching off to infinity at the linear speed. And this function that to n assigns the G to the n of x0 is a quasi-isometry onto its image. So coarsely you see that there is this set where G is translating, shifting these points by one unit, and that somehow is the analog of the loxodromic transformation of the hyperbolic plane. And then also to a topologist like me, what's kind of interesting is the fact that every hyperbolic group has a boundary called Gromov boundary. It's a compact metrizable space, and it's obtained by taking, say, fixing a base point, and then looking at geodesic rays that go off to infinity. So a point at infinity is going to be an equivalence class of such rays, where two rays are equivalent if they stay bounded distance apart. And so in the case of the hyperbolic plane, you get the circle boundary. So any fundamental group of a surface of genus at least 2 is going to have Gromov boundary, the circle. And on the other hand, the free group, like F2, is going to have Gromov boundary, which is a Cantor set, because that's the boundary of a tree. And then I will also mention this as a kind of a curiosity, but if you could wonder what happens with those random groups. What's the boundary of a random group? Well, here's the picture. It's a Menger curve. So these boundaries can be fairly complicated topologically. They don't have to be just like a Cantor set or a circle, which makes it interesting. Okay. The next thing I want to talk about is what I think of as being the most basic invariant of metric spaces up to quasi-isometry. So what are the quasi-isometry invariants of metric spaces? How can you tell that two metric spaces are not quasi-isometric? Well, in topology, we have the covering dimension that's, well, maybe arguably the simplest homeomorphism invariant. And so the analog here is the asymptotic dimension. And the definition is due to Gromov. And you can, as you can see, the definition is motivated by covering dimension. You have to adjust the quantifiers a little bit, but it's certainly inspired by the usual covering dimension definition. So what's the definition? Well, so X is a metric space, and we'll say that asymptotic dimension of X is less than or equal to n is some given integer, if and only if for every number r, and you should think of r as being large, you can find a cover UI, and it can be open, but it doesn't have to be open. That's not very relevant here for these large sets. You can always replace them by open sets if that's what you want. So there's a cover UI of X, so that there are two properties. Well, first of all, these sets have to be uniformly bounded. That is, if I look at their diameters, well, there will be infinitely many numbers here. Well, the soup has to be still finite. And then the key thing is that if I draw the any metric R ball in the whole space, then I will never intersect more than n+1 of these sets. And so here's the picture of the plane, and this picture shows that the asymptotic dimension of the plane is at most 2. So you take this brick decomposition of the plane. So I have these horizontal lines, and then strips between horizontal lines are subdivided into squares. Okay, so these are my UIs. And you can see that they all have the same diameter. They can slowly choose them so that they all have the same. They're all isometric to each other. And if I draw a metric R ball, well, it will look like this blue ball here. Well, you might complain that's what if the ball is larger? Well, then I can just draw the bricks larger. So everything is kind of a scale invariant here, and this picture shows that asymptotic dimension. So the blue ball will intersect at most 3 bricks. And so that shows that the asymptotic dimension of the plane, Euclidean plane, is less than equal to 2. Okay, so here are some basic properties of asymptotic dimension. Well, so the asymptotic dimension is QI invariant. If 2 spaces are quasi-isometric, then they have the same asymptotic dimension. So for example, the asymptotic dimension of z to the n is equal to the asymptotic dimension of Rn. And I showed you the argument that shows that it's less than or equal to n, but in fact, they're equal to n. Any tree has asymptotic dimension at most 1. That's maybe a good exercise. It's not completely obvious. Gromov proved that for any hyperbolic group has finite asymptotic dimension. And that's interesting for several reasons. I mean, well, you could say it's, so the important reason is this theorem of U that says that if a group G has finite classifying space and its asymptotic dimension is finite, then G satisfies this Novikov conjecture from topology of manifolds. But also somehow if you're out there to understand the coarse geometry of a group, then you should presumably be able to tell what its asymptotic dimension is. Just like if you're studying a topological space, if you don't know what its dimension is, then that doesn't seem like you understand it. So so certainly from this kind of philosophical point of view, this is an important result. Also, it passes to it's monotonic with respect to subgroups. If H is a subgroup of G, well, then asymptotic dimension of H is less than or equal to asymptotic dimension of G. That follows quickly from definitions. And just to make the subject more interesting, there are even finitely presented groups whose asymptotic dimension is infinite. So, for example, Thompson's group is such a group. It contains z to the n for every n, and so this monotonicity implies that asymptotic dimension of Thompson's group is infinite. And so this also shows that some of hyperbolic groups are much better behaved than arbitrary groups. All right, so now we're going to shift gears a little bit. We'll talk about mapping class groups. Okay, so just to remind everybody of the definition, in this talk, the surfaces are going to be, well, most of the time closed and oriented, but if you want, you can also subtract a finite set of punctures. Okay, so then the mapping class group, what is the mapping class group? Well, you take all orientation preserving homeomorphisms of your surface and you mod out by isotopy. Isotopic homeomorphisms are considered to be equivalent, or equivalently, you can also mod out by homotopy instead of isotopy. Homotopic homeomorphisms are going to be isotopic in this context. Okay, so for example, the two-sphere has the trivial mapping class group, which is certainly hyperbolic. It's not very interesting. The torus has a more interesting mapping class group, but it is still hyperbolic. It's SL2Z. SL2Z contains a finite index subgroup, which is free. And so the SL2Z is also hyperbolic. But most of the time, these mapping class groups are not hyperbolic. And to see that, you can you recall what a Dane twist is. So Dane twist is really a homeomorphism of an annulus, pictured here. And the homeomorphism is identity on both boundary components. So you take, here's one boundary component, here's the other one. And in between, on these circles, concentric circles, it will rotate them. So it'll start at the inner boundary component, it'll start by rotating by 0. And on the outer boundary component, it will rotate by 2 pi. And so a segment like this horizontal segment, will end up being mapped to as kind of a spiral like this. It's an arc with the same endpoints, but it will go around the annulus once. So that's Dane twist. And if you want to be pedantic, you can talk about left Dane twist and right Dane twist. Okay, so now if you have a surface like, say, genus 2 surface over here, then you can embed the annulus in 2 different ways. Say I have a red annulus here and a blue annulus, and you can put this Dane twist on each annulus so that in the complement, the homeomorphism extends by the identity, and on the annulus, it's a Dane twist. So these are 2 different homeomorphisms, one for each annulus, and they obviously commute because they have disjoint supports. And they will give you z squared inside the mapping class group, and therefore mapping class groups are not, this mapping class group is not hyperbolic. For the torus, you just don't have enough room to put 2 disjoint annuli in this way. Another importance of Dane twist is that they generate the mapping class group, and this is by work of, classically by work of Dane, and then Licorice, and then most recently Humphreys. We know that we have a very, very small list of Dane twists that generate the mapping class group. So here you have so in the genus G surface, you'll have G of these blue curves, and then you'll have G minus 1 of the red curves, just connecting adjacent holes in this surface. And then you'll have 2 more. Just 2 more for whatever the genus is. So this alpha 1 and alpha 2. Those are those suffice to generate the whole mapping class group. And the mapping class group typically will have torsion, but if you pass to a subgroup of finite index which is torsion free, which is always possible, then these subgroups will have a finite classifying space, just like hyperbolic groups. And if you don't want to pass the finite index subgroup, then they'll have these finite classifying orbifolds, where finite subgroups appear as stabilizers of points. There are many classical results here. I just want to feature one more, namely the work of Thurston that builds on the classical work of Nielsen. And it gives you a normal form for the elements of the mapping class group. So this is somehow analogous to a Jordan normal form for matrices. Here on the left, we see a typical building block. So the building blocks are called pseudo-Nassau homeomorphisms. And what they have is they come with 2 foliations with certain kinds of singularities, but the foliations are transverse to each other. So if you look at the red leaves, they're always in this. They should be perpendicular, really, with the suitable metric on the surface. The blue leaves and the red leaves are certainly transverse, except at these singularities. And if you take a little rectangle bounded by the 2 foliations, it will be mapped to another rectangle bounded by the foliations in such a way that one of the foliations gets stretched by a certain factor lambda called dilatation, and the other foliation gets squeezed by the same factor. So the area remains the same. So this U gets mapped to a rectangle f of U of the same area, but it gets stretched in one direction and squeezed in the other. Okay, so those are the building blocks, and a more typical mapping class is going to have a canonical decomposition of the surface pictured here on the right. So here's a potential decomposition. Some of the pieces are annuli, and they're going to support a Dane twist or a power of a Dane twist. And then these other pieces are going to support either one of the pseudo-nosubs or a finite order element. So some kind of a finite, so rotation of some kind. And then more generally, the homeomorphism might permute the pieces, so that the first return map for each piece is one of these. It's either finite order or pseudo-nosub or a Dane twist, or power of a Dane twist. Okay. Okay, so next we come to the notion of the curve graph. This was defined by Harvey in the 70s, and it plays a key role in what I'm going to describe in the second part of the talk. Okay, so the curve graph is associated to a surface. Okay, it's a certain graph, or even you can make it into a simplicial complex, but we'll really only care about the one skeleton here. So we'll think of it as a graph. So a vertex of this graph is an isotopy or equality homotopy class of essential simple closed curve. So let's think closed surface. If in the closed surface, essential is the same as not null homotopic. So you want a curve that doesn't bound the disk on the surface. And you put an edge between two such vertices if the corresponding curves can be homotoped to be disjoint. Okay, so in this picture, I have, for instance, the blue curve and the pink curve are already disjoint. So blue and pink are connected by an edge. On the other hand, the blue and the green are not connected by an edge because they intersect. Well, here you have to prove something. You have to prove that there's no homotopy that makes them disjoint. So this is not meant to be completely obvious, but this is true in this picture. Okay, so this is just some small subcomplex of the curve graph, some small subgraph of the curve graph. The picture can be drawn for the case of a torus. So in the case of a torus, we have to modify the definition slightly because we don't have essential curves. If you have two essential curves that are disjoint, then they will be parallel. They will really represent the same vertex. So here, the best you can do is say that you're going to draw an edge if the two curves intersect in one point, because that's the minimal possible intersection number between two curves that are both essential and not homotopic to each other. Okay, so the curves, simple closed curves on the torus are classified by their slope, and those are rational numbers, and you can see them pictured here on the along the circle. And then so for example, a blue curve here has slope 0, and it corresponds to this vertex here, and the red curve has slope infinity, and it's over here. And since they intersect in one point, then there's an edge connecting them. And more generally, if you have two rational numbers p over q and r over s, you join them by an edge if the determinant made up of these four numbers is plus or minus 1. So this is the classical theory graph from number theory. And you can already see certain features here. For example, the theory graph is not locally finite. Every vertex is connected to infinitely many other vertices. Okay, so what are some features of this construction? Well, the mapping class group will act on the curve graph because it will take an essential curve. Any element of the mapping class will take an essential curve and map it to some other essential curve, and the disjointness will be preserved by any element of the mapping class group. And as I said, they're locally, so these curve graphs are locally finite. And then Kobayashi proved that the curve graph has infinite diameter when the surface is complicated enough. So when, for example, when the Euler characteristic is less than -1. One other thing that you might notice, by looking at the photograph, is that it is hyperbolic, and not only hyperbolic, it is quasi-isometric to a tree. And that's also not obvious, but it's also a good exercise. Okay, so then we arrive at the year around 2000, and this groundbreaking work of Mazur and Minsky. They showed that the curve graph is in fact hyperbolic for any surface S. The curve graph is going to be hyperbolic, and the pseudo-Nassau mapping classes. Those are the ones, the building blocks in the Nielsen-Thurston classification. They are loxodromic when they act on the curve graph. And the other elements of the mapping class group, the ones that are not pseudo-Nassau, so the ones where the subdivision into either finite order or subdivision of the surface into subsurfaces is non-trivial, those are all elliptic. Okay. So, for example, you can see that the Dane twist is going to act elliptically because it will fix many curves, right? It will fix any curve in the complement of the angle where the Dane twist is happening, or even more simply, it will fix the curve right in the middle of the angles, or on the boundary of the angles. And this theorem somehow caused a sort of philosophical shift in the subject. This is where we realized that we should be studying actions of groups that are not necessarily hyperbolic on hyperbolic spaces or hyperbolic graphs. They're also not necessarily locally finite, because there are natural examples of this that occur certainly for mapping class groups, but also for other groups. And so here you could ask, what about mapping classes that are not pseudo-Nassau? For example, Dane twists. Can we have an action on some kind of a hyperbolic space so that Dane twists are also loxodromic? We'd like to see them. The elements that are elliptic are not really seen by the action. They somehow, we think of it as fixing a point. Elliptic elements have finite orbits, and they might not really fix a point, but coarsely we think of that as having a fixed point. And so, if you want to see all elements, we'd like to have the feature that every element of the mapping class group of infinite order acts loxodromically on some hyperbolic space. Okay, so we'll return to this question, but let me now start on the construction of hyperbolic spaces. So this will lead us to projection complexes. So here's a fairly common situation in geometric group theory. If you go to some conference in geometric group theory, then you're bound to see this kind of a picture being drawn by the speakers or some of the speakers. So we have a genus 2 surface here, and then we have this curve, which you can think of as being a geodesic, a simple closed curve in the surface. And we look at the universal cover of the surface, and that's of course hyperbolic plane, drawn as a Poincaré disk. And we look at the full preimage of this simple closed curve. So we get all these red lines. So here's one, and so on. There are infinitely many red lines that are components of the preimage of this curve under the covering. And just to set up some notation, this script y is going to be the set of all these red lines, the set of all these lifts of the curve. And if I take two of them, x and y, then I can nearest point project one to the other. Okay, so for example, here's the line x, and here's line y. And what I do is I drop the perpendicular in the hyperbolic plane from the endpoints of this line y. So this green thing is supposed to be a geodesic that's a perpendicular to x, and this is the other one. And then the nearest point projection of y to x is this segment here, this blue segment subset of x. Okay, so that's denoted by pi sub x of y. It's the projection of y to x. Okay, we always think nearest point projection. Okay, so now the game is, so what happens if I just give you this data here? I give you the collection of lines, script y, and I give you pi x of y for any two lines x and y distinct from each other. But I don't give you the ambient space. I suppress that when I give it to you. So this is called the projection data. Okay, so we have this set y of lines, and they're viewed as metric spaces. So in this case, they're all isometric to R. And then we also have these non-empty subsets, pi x of y, contained in y. Right. So for any two, I see there's already a mistake. There should be x. Okay. So for any two lines or metric spaces x and y, I have this projection of one to the other, and it gives me a subset of the metric space you're projecting to. Okay, if given that, we can talk about the projection distance. So given three of these lines, x, y, and z, I can project both y and z to x, and then so pi xy and pi xz are going to be two segments. So here in the picture, right? So here's x, and then there's y, and there's z, and I can project both y and z to x, and I'll get these blue segments like so. And then I can take the distance between them. I can think about taking the union of the diameter of the union. So that's sort of the distance between y and z as seen from x. And that's what this quantity here is. And then there are three properties that you can check in this situation. Well, first of all, the diameter of these projections is uniformly bounded by some number theta. Then the second one is the so-called Berstock inequality, and it says the following: that if you give me three lines x, y, and z, and then you can form three of these numbers. You can look at the distance in x between y and z. You can look at the distance in y between x and z, and you can look at the distance in z between x and y. Well, the Berstock inequality says that two of these numbers are uniformly bounded by, say, this number theta. Only one can be big. Okay, so for example, if this one is big, then this one here has to be less than or equal to theta. And then finally, there's a finiteness axiom that if you fix y and z and you wonder how many of these x's there are, so that the projection to x is big. So that set is finite. And there are only finitely many x's for fixed y and z, so that the projection to x is big. Okay, so here's maybe a simpler setting where you can check these axioms. So yeah, I'm replacing the hyperbolic plane by a tree, and then y is going to be the set of horizontal lines in this picture. So these red lines, that's my set y. And now the nearest point projection really gives me just a point. If I take say this red line and I want to project it to this red line, well, I'll get this point here. Okay. And here, the claim is that axioms actually hold for theta equals 0. And here's the verification of the Berstock inequality, the P2, I call it. So here you have a line x, and you have two lines y and z, so that the projections are distinct. So the distance between y and z viewed from x is bigger than 0. Well, then you can see easily that, for example, when you project x and z to y, you get the same point, right? So the projection of x to y is the same as the projection of z to y. Okay. Okay, so the theorem about this setup is, so this is joint work with Ken Bromberg and Koji Fujibara, and these are my partners in crime over here. So roughly speaking, it says that if you have just projection data without the ambient space, and P1 through P3 are satisfied, then you can build an ambient space so that these projections are realized up to a uniformly bounded error. Okay, so this is the simple version of the theorem. Here's the more elaborate version. So, so given projection data satisfying P1 to P3, you can build an ambient space Y. So this is the boldface Y. So that the space contains pairwise disjoint isometrically embedded spaces from your collection. So you're for instance, for these lines, you find a space where these lines are embedded in a pairwise disjoint way, and they're all isometrically embedded. And you can form projection, nearest point projections in this new space. That's this pi sub x boldface Y. And then there's also pi xy. Those are the projections that are given to you. Well, they're within uniform distance of each other. So you're making some kind of a uniform error everywhere, but it is a uniformly bounded error. Right? And in coarse geometry, this is allowed. And then maybe the critical thing here is that if all these spaces that you're considering, like these lines, if they're all delta hyperbolic with the same delta, then the space you're building is hyperbolic, and that's going to be our new space that we're after. We're building a new hyperbolic space in this way. The relation with asymptotic dimension is that if you, for example, if there are only finitely many isometry types, so for example, if they're all isometric to a line, and asymptotic dimension of each of them is less than or equal to n, then the asymptotic dimension of the space you're building is just maybe one more, n plus one. And this picture somehow suggests how this is done, although it's the details are more complicated. But essentially, these red blobs represent the spaces in the script Y. And then they're going to be connected by collections of edges in a certain way. So there's some way to decide whether two of them should be connected by an edge or not. And then if you decide that you should connect them, then where do you put this edge? Well, you look at the projection of each of them to the other one, and that's going to give you a bounded set. And then you put an edge or a collection of edges between the points in those bounded sets. And one feature of this is that if you mod out all these red blobs to points, then you get a tree. You get something that's quasi-isometric to a tree. So it's a quasi-tree. So you should think of this space as being some kind of a quasi-tree of metric spaces. And this construction is equivariant. There are you don't really make too many choices. If you have a group acting on the data here, then and preserving the data, so it's acting on the collection of metric spaces by isometries. It doesn't have to preserve any of them. You can send one to another, but by an isometry. And it commutes with these projections. Then, in fact, the same group will be acting on the resulting space. And so, in the situations when the resulting space is hyperbolic, this gives us a potential interesting action of your group on the hyperbolic space. Okay, so now let's return to mapping class groups. Okay, so here S for simplicity is going to be a closed orientable surface. I'm going to ignore punctures as much as possible. And then what's a subsurface? Well, it's a compact connected pi1 injective subsurface. When I say subsurface, I will always assume that it's compact connected and pi1 injective. But there are two exceptions. I don't want a disk, and I don't want a pair of pins. So this is the sphere with 3 holes. Those are bad because they don't have a curve graph. The others do. Okay, so in this picture here, I picture 2 subsurfaces. So there's a genus 2 surface, and then there's kind of a left subsurface X, sort of pictured in blue, and then there's the bottom half. The bottom half is Y. And we are going to write that X is transverse to Y if boundary of X, which is this blue curve here, intersects Y, and boundary of Y intersects X. And so that, for example, this curve here intersects X, and this curve here intersects X. But Y has 3 boundary components. So this is, of course, even after isotopy. So you're supposed to put them in minimal position with respect to each other, and then these intersections have to be known. And so then that's when we say X and Y are transverse. So we don't want disjoint subsurfaces, and we don't want nested subsurfaces. Okay, in those situations, you can define a subsurface projection. So this is one of these constructions of Maser-Minsky. You can project the curve complex of Y to the curve, or curve graph of Y to the curve graph of X. Okay, so here's how it works. So this X is really, that was the left half of our surface, and I'm drawing it over here, and I'm also drawing the boundary, the intersection of the boundary of Y with X. So here you're just going to get, you'll get this closed curve here, and then you also get this arc when you intersect. You get this red arc. Now the red arc is not really a simple closed curve, so it doesn't define a point in the curve graph of X. But what I can do is I can close it up. I can close up the endpoints along the boundary of X. And there are two ways to do it. You can either use this arc at the top, or you can use the arc at the bottom. And so looking at all these choices, you have, there are three curves here. You can use the boundary component of Y that's already contained in X, or you can do this closing up business in two different ways. So you'll get three curves, and there in this picture there are three disjoint curves, and therefore they define a subset of 3 points in the curve graph of X that has diameter 1. So it's a bounded set. Okay, so that's somehow is promising, and that's basically this property P1 that projections have to be uniformly bounded. And more generally, from the Maser-Minsky theory and from the work of Baerstock, and then maybe we added a little bit, is that if you have a collection of subsurfaces that are pairwise transverse, okay, so it's important that they're pairwise transverse. If they're disjoint, then there's no notion of a projection of one to the other. But suppose you have a collection of subsurfaces that are pairwise transverse, then the collection of corresponding curve graphs, so C of X's curve graphs, and these subsurface projections, they satisfy P1 to P3, satisfies those axioms. And here, the thing is that there's no ambient space you started with. This is just a kind of a notion of projection of one to the other, but there's no nearest point here. There's no ambient space that's given to you ahead of time. And so here's an example. You can take a surface of genus 3, and you can take X to be the subsurface of genus 2. And it's not too hard to see that the orbit of X under the mapping class group consists of pairwise transverse subsurfaces. You cannot have two disjoint subsurfaces of this type because there's not enough room, and you cannot have nesting. And so if you apply this construction to the orbit, you're going to get an action of the mapping class group on some new space Y that you didn't have before. But now if you take an element that's pseudo-Nosov on X. So remember, there are these. There is this Nielsen-Thurston decomposition, and I could choose my decomposition of S to be this X together with the complement, and I can put a pseudo-Nosov on X and identity on S. Now that mapping class acts elliptically. For example, it fixes this curve. It acts elliptically on the curve graph. But it will act loxodromically on the space that we just constructed, because say in this picture here, one of these blobs is the curve graph of X, and so the pseudo-Nosov on X will act by some kind of it'll be acting loxodromically. There's going to be some line, quasi line that's where this mapping class just translates. Another fact we will need is that there's an equivariant partition of the set of all subsurfaces of S up to isotopy into finitely many classes, so that within each class, any two subsurfaces are pairwise transverse. This is illustrated in this picture of the Ferri graph, which represents the collection of subsurfaces of a punctured torus, each of which is an annulus, and we can equivariantly color the vertices of the Fourier graph so that each triangle gets all three colors, red, blue, and green. Okay, so now to recap, we have this finite partition of the collection of subsurfaces into these SIs. Each SI is going to give us a hyperbolic space by the construction of projection complexes. And since the mapping class group permutes the partitions, it will act on the product of these spaces, yi, y1 to yk. And it follows from the general Maser-Minsky theory that the orbit maps of this action are in fact quasi-isometric embedding. So you get a subset of this big product, which is quasi-isometric to the mapping class group. And we also understand the image of this map. This is by the work of Berstow, Kleiner, Minsky, and Moser. And then the final fact we need is that curve complexes all have finite asymptotic dimension. So again, by the general theory of projection complexes, this means that all these spaces yi are also have finite asymptotic dimension. And therefore, the mapping class groups also have finite asymptotic dimension. That's sort of a corollary of this. Okay, so for the end, I just want to mention some open questions. The first two are about just hyperbolic groups, and they're very classical. The first question is, are hyperbolic groups tangentially finite? This means that if you intersect all finite index subgroups, you get a trivial group. The second question is, that if you take an infinite hyperbolic group whose boundary is connected, so for example, free group is not allowed, then does this group necessarily contain a hyperbolic surface group as a subgroup? And then finally, the last question is about RFN. The basic question is whether we can run the same program as we did for the mapping class group to establish that asymptotic dimension of RFN is finite. So there are several pieces of this program that are already in place. We do have hyperbolic RFN complexes analogous to the curve graph, by the work of Handel, Moser, and my work with Fein, they're hyperbolic. But we don't know that asymptotic dimension of these complexes is finite. And so we also have these projections. There are subfactor projections instead of subsurface projections, but we end up with an action about Fn hyperbolic spaces. We don't know that these hyperbolic spaces are finite asymptotic dimension because we don't know that the building blocks, namely these hyperbolic complexes, have finite asymptotic dimension. And then in addition, we definitely know that the orbit maps are not QI embeddings. And so to complete this, we would have to understand what you might think of as the fibers of this map. All right, well, thank you for your attention. This is the end of my talk, and I hope to see you at some point in the future in person.
Okay, Mladen, thank you. That was a great talk. And I'd like to thank everybody who tuned in. So, goodbye.